descriptions of waves you guys gave, any of them that had to do with things like sound or water or things where the wave travels through something, that's a mechanical wave. So a mechanical wave is any wave that requires a medium. Any wave that requires a medium. And a medium is simply a substance that a wave propagates through. A medium is a substance that a wave propagates through. All right, so for example, yeah, I will. For example, if Rory and I are in space and I'm yelling at her, will she be able to hear me? No, why not? There's no air. So specifically, there's no medium for sound. So sound must be a mechanical wave because it needs a medium to travel through. Good with that idea? All right. So within mechanical waves, we're going to talk about three different subsets of waves. The first one are transverse waves. Transverse waves. A transverse wave is any wave in which the particles move perpendicularly to the direction of motion of energy. Any wave in which particles of the medium move perpendicularly to the direction of motion of energy. Move perpendicularly to the direction of motion of energy. Okay, so that means that if we're talking about, say, a wave moving down a rope, if you snap the rope, then the energy moves down the rope, but the rope itself just moves up and down or left and right. I'll demonstrate some of this in a few minutes. One of the easiest ways to draw out a transverse wave is just make it look like what we would call a sine or cosine function in math. So I'm going to draw a dotted line to represent where it started. And each of the different spots along the wave has a specific name. So the top ones we're going to call a crest. So a crest is the high point of a wave. High point of a wave. And the lowest point is called a trough. Trough. Low point of a wave. And the distance from the median or from the rest position to the crest or to the trough is what we call an amplitude. And amplitude, which we can just say the height of a wave. Now, every year, I put a question on the test that asks you to draw or label an amplitude on a wave. And every year, I have somebody draw me a line that goes from here to here. Don't be that person, okay? Make sure you're clear that the amplitude is from the rest position or the middle point to the top. Or you can go from the rest point, the middle point, to the bottom. You can't do both. That's twice the amplitude. Okay? Good with that? Nobody's going to be that person? All right. Next one that we can draw on our wave is the wavelength. Wavelength is the distance between any two identical points on a wave. Wavelength. Now, you may hear it called the wavelength identified as crest to crest or trough to trough, and that's right, but it leaves out a whole bunch of possibilities. Sure, I can go crest to crest. I can go trough to, well, trough's going to be over here off the paper somewhere, but I could also draw a wavelength from here to here. showing that it's at this point that's going up to this point that's going up. Not here to here. Those aren't identical points. This one's coming down, that one's going up. Here to here, they're both going up. Okay, so wavelength is the distance between two identical points on a wave. The distance between two identical points on a wave. Okay. Wavelength is measured in meters. Measured in meters. And uses the Greek symbol lambda in equations. So that'd be this thing. It's kind of an upside down y in equations. All right, questions so far? Good. All right, we've got three more. Three more definitions specifically for transverse waves. Fortunately, with wavelength, these other three apply to all types of waves, regardless of whether they're transverse or even mechanical. So next up is the period. Now, I can't draw a period on my diagram up top because period's an amount of time. Period is specifically the amount of time it takes for one wave to go by a single point. The amount of time for one wave to pass a single point. A point. Okay? Since it's an amount of time, we're going to measure this in seconds. And period being time uses capital T in equations. And is measured in seconds. Okay. Next up, we have frequency. Frequency is a number of waves that pass a single point in a second. The number of waves that pass a point in a second. All right. In equations, it's going to be the letter F and is measured in hertz. Which is abbreviated Hz. All right. After you've got all that down, take a second and go back and read over period and frequency. I want to know, are they similar in any ways? And what? What ways? How are they similar? Or how do they seem to be related? How do these two seem to be related? All right, so using those three things, one of the individuals in fifth hour was able to point out that they sound kind of like opposites of each other. And in sixth periods, one of them pointed out that, just like McKenna pointed out here, that one's paying attention to an amount of time for one wave, and the other is paying attention to an amount of waves in one piece of time. So yeah, they're kind of opposites of each other, or inversely related. And actually, if we're looking at an equation, t for period is equal to 1 over the frequency. So that also means that a hertz, 1 hertz, is equal to 1 over 1 second. Okay? So frequency and period are just the opposite of each other. They're just inversely related. And the last one that we've got to add on here is wave speed. And wave speed is simply how fast a wave travels from one point to another. How fast A wave travels from one point to another. All right, so if you are that amplitude was not only the height of the wave, but it also shows us how much energy the wave has. Shows how much energy the wave has. And then under wave speed, we need to put in that it only depends on the medium. Only depends on the medium. So while the relationship between wave speed and wavelength and frequency is that v, where v is wave speed, is equal to frequency times wavelength. Yep. If I increase frequency, I don't increase the speed of the wave. What do I change if I increase frequency? Yeah, what else happens since I can't change the speed of the wave? Just working with that equation. What has to change if speed can't change, but I do change the frequency? Say again? The wavelength. So as I increase frequency, I must decrease wavelength. And you saw that. When we sent those quick waves, they were short. But when we sent the slow waves, they were long. They all traveled at the same rate, but as we changed the frequency, we also changed the wavelength. All right, questions on any of those? That brings us to our next type of wave, which is a longitudinal wave. All right, a longitudinal wave is basically the opposite of a transverse wave. Where a transverse wave, the particles of the medium move perpendicularly to the direction of motion of the energy. A longitudinal wave, the particles of the medium must move parallel to the direction of motion of the energy. Particles of the medium move parallel to direction of motion of energy. Of motion of energy. Now, drawing this one out is not as nice, so I just try to draw the slinky version. And I tried drawing this spaced out initially, and then I'm going to try to bunch them up and space them out and then bunch them up again. And a longitudinal wave doesn't have a crest or trough because it doesn't have a height. So you can't have the highest or lowest point. What you can have are the compressed and spread out points. Now, a spot that is compressed or has a higher density is going to be what we call a compression. And these portions that are more spread out are what we call rarefactions. Now, a longitudinal wave can also be called a density wave or a compression wave, aka density wave or compression wave. And it has to do with the fact that, well, as a wave travels longitudinally, it changes the density of the medium. So as I'm talking to you guys, I'm sending longitudinal waves to you. Sound is a longitudinal wave, meaning that at different points in the air, the density of the air has been changed because I'm compressing it with my voice. That's how that actually travels to our ears. Okay. Now, in terms of the other variables, wavelength, period, frequency, and velocity all behave the same, all work the same. Okay, so surface waves. Now, a surface wave exists between a barrier between two mediums. So when we talk about this for water, really it's because water and air are two separate mediums and they're in contact with each other. So it occurs where two mediums reach each other or meet each other. Two mediums meet each other. And a surface wave combines the motion of longitudinal and transverse waves to create a more circular kind of motion. Combines longitudinal and transverse motions. So if I've got a wave here, I'm going to go with a water wave, and I put a bobber on it. All right, where are my fishermen or fisherwomen? Anybody? Do I have any? One, kind of. Two? Okay. So when you go fishing and you use a bobber, if you cast the bobber into a lake that doesn't have any current, where does the bobber go? Does it float in towards you? Does it float out further? What's it do? With no current. Yeah, just no, it wouldn't sink, but it would just stay there. It's not going to go anywhere. Now, when you cause waves, maybe that's because a boat went by or a fish broke the water or your younger sibling threw a rock in next to it. Those waves are going to pass under the bobber, and the individual particles of water aren't actually going to go very far, and neither is the bobber. The bobber is going to go forward and back, but it's going to oscillate around in a circular-like motion as it's combining the transverse motion and the longitudinal motion that the other two types of waves have. So it's never going to actually travel in to get to you or out further. It's just going to bob around in about the same location. Okay? It's only when we actually have a current that bobber starts to come in closer to us or drift out further from us. Okay? Questions about surface waves? Okay. So energy travels from one point to another, but particles of the medium move in a circle. Travels from one point to another, but particles of the medium move in a circle. Of the medium move in a circle. All right, so what I want us to do with the last bit of time here is I want us to take a look at a very large example of a surface wave, a tsunami. Now, video I've got for you here